All right, what's up? Um, Welcome back. Today we're going to look at the Linux kernel source code. I've been doing a series of these where I'm just poking around at different code bases from mostly kind of complicated open source projects to kind of get a feel for how they work. Um, I've also been um, bit by bit trying to improve some of the video and audio quality issues I've had. Hopefully today the font on my browser should look a little bit better. We'll see how that goes when all the encoding happens. Um, and I've simplified the audio setup a bit, so hopefully there won't be as much of an audio delay. I've tried in the past to account for the delay by various means, but it's never quite been to my satisfaction. So I'm hoping by just simplifying the audio chain, I can get somewhere closer to where I want to be. So the Linux kernel source code. I haven't looked at the kernel source code. I've used the kernel a lot. I've compiled kernels in the past, but not really trying to understand anything that's going on inside the code base. So let's take a look at what they got. And I noticed that when I looked at this right before the stream, it tells me that the first thing I should do is read documentation admin guide /readme. I'm tempted not to do that, just out of defiance, but I will do it, and I have it open here. It's relatively short. So let's just take a quick look at what's going on. And that tells me what Linux is. I already know what it is. What hardware does it run on? Okay, let's see if there's any surprises here. I don't know a lot of these. Like, I don't know what Hitachi Super H is or Cell, but seems good. There's documentation and installing the kernel source. And yeah, I guess we have to unpack it with XZ and do a bunch of stuff. And this is software requirements, how to build it and how to configure it. Do not skip this step if you are only upgrading one minor version. Okay. Make rand config. Create a config file by setting simple values to random values. Actually, that's a really good thing to have. I would suspect it's mostly for testing, because you're not going to be able to enumerate all of the combinatorial possibilities for different configs. So if you can randomize it, then at least you have a chance of testing configs that are kind of walking around the config parameter space. So that's nice to see. Compiling the kernel. Okay, great. That's pretty basic stuff. So let's take a look around. So I see Rust here. I think the Rust stuff is pretty new, so I guess I'll poke around there. Crypto. I guess I will look there. Let's see. Block, inserts, crypto drivers. FS, I assume, is file systems include. This might be where all the header files are. Init. Is this I'm assuming this is the kernel init. Let's look at init. I want to see the IPC. I want to take a look at the kernel directory and lib. And maybe net. And security, I guess, is different from crypto. Actually, I'm going to do this. Security, sound, tools, user, and vert. Okay, we're not going to be able to look at all of this in one go, at least not in any depth. But we can at least, as I say, poke around. Actually, let me adjust something here. I have a feeling that I'm only going in one side here. Okay, so let me try adjusting one more thing with respect to the audio that I just noticed, because, as I said, I have a new audio setup. Um, let me try bumping. I changed it to stereo. I'm going to bump the makeup gain again because my level dropped down. So hopefully, this is not too loud. Well, I guess we'll find out. We'll find out. But at least the levels don't look like they're clipping. Okay, so where are we? We're in Rust. So there's not a lot that's gone on in Rust yet. Okay, so alloc bindings, kernel, macros. I'm going to pull Rust into its own frame here. Okay, so in kernel, there's a relatively small number of stuff. I think this is consistent with what I had seen from wherever I was seeing things that basically they're starting very small with Rust macros. Let's find out what these macros are. Oh, I want to see vtable. Oh, never mind. Okay, where am I? I'm at the module.rs macro. I don't see any code comments. What makes this a macro? Proc macro token string literal. So is macro a Rust thing? Does Rust have macros? Macros, hey. We've used macros like println throughout this book, but we haven't fully explored what a macro is and how it works. The term macro refers to a family of features in Rust, declarative macros with macro rules, and 3 kinds of procedural macros. All right, cool. I'll read this later. All right. So that's all fun. So I guess these are macros that are used in the kernel code base. But this is bindings, lib.rs. Imports the generated bindings by bindgen. This crate may not be directly used. If you need a kernel C API that is not ported or wrapped in the kernel crate, then do so first instead of using this crate. Okay. So I can't read Rust yet, I don't think. I've written a few lines of Rust, and I think I've read the Rust book long ago, but I don't really remember how a lot of this goes. But there's some include thing. Is the bang a null safety assertion? Let's see. That's a standalone exclamation mark. Will this tell me? Or is it a macro? I don't know. Okay. So this is going to include something or other, and it's got obtree Rust bindings generated. So use glob import here to expose all helpers. Symbols defined within the module will take precedence to the glob import. Okay, so this is importing, this is doing some glob import, which is, I guess, okay. It's a little bit, so globs are a little bit weird because that means, I guess that that what you import kind of depends on, things aren't listed explicitly. So you can maybe sometimes run into bugs that are a little bit hard to figure out if you do things like import by globs. But I think the kernel people know what they're doing. I think they run a pretty tight ship. Okay, here's Rust alloc. These source files come from the Rust standard library. Is this for allocators? On one hand, kernel folks wanted to keep alloc in tree to have more freedom in both workflow and actual features if actually needed, e.g. receiver types if we ended up using them, which is reasonable. On the other hand, Rust folks wanted to keep the alloc as close to upstream as possible and avoid as much divergence as possible, which is also reasonable. We would keep a set of alloc entry that would be as small and as close as possible to upstream. Then upstream can start adding the functions that we add to alloc, etc., until we reach a point where the kernel already knows exactly what it needs in alloc, and all the new methods are merged into upstream so that we can drop alloc from the kernel tree and go back to using the upstream one. Okay. That seems pretty reasonable. Although you would think that maybe there's some utility that copies. This is essentially the same as vendoring alloc in some sense. So usually I think there would be some mechanism to synchronize periodically, perhaps being kicked off manually to synchronize the alloc stuff here with what's upstream. But I'm not going to look into too much about whether that's the case. Okay, so here's crypto. Let's just quickly glance at this to see if there are any surprises. Kconfig, I assume, is a kernel-specific config. What's the SPDX license? Oh, it's an identifier. GPL 2.0 is the license. Okay. So this is configure information. Cool. We've got AES, AEAD. Do they write their own crypto implementation? Maybe they have to. Copyright 2007 to 2015 by that guy. Export symbol GPL. Okay. Yeah, this doesn't look like it was copied from anywhere. Okay. All right. So Anubis. What is Anubis? The Anubis algorithm was developed by Paolo Barreto and Vincent Rijman. Okay, so there's something about S boxes and Anubis. This looks like it may be an S box. Okay. And a bunch of other algorithms. This none of this is really surprising. All right. Okay, so what's an include? Let's see. I'm curious whether, yeah, okay, so this looks like it's all a bunch of headers. I'm not sure what's the reason for having a separate include directory? Is it because a lot of the tooling you point at a directory, and this makes it easier to just pull out the headers? Okay, so here's KVM. It's got a bunch of ARM stuff. Clock source. Timer goldfish, timer risk fee. Interesting. Okay, so it looks to me like there's maybe less, or I guess fewer files in some of these directories than I would have expected given the complexity. So I'm not sure if this is all of the headers or if there's less complexity than I anticipated. Let's take a look at init. So there are headers kind of sprinkled through here every so often. Yeah, I'm not sure. I'll have to... I wonder if I go to the commit, can I blame 15 years ago, 18 years ago? I wonder if I can figure out why they decided to, wait, am I looking at the header here? Yeah, include this header outside of the include directory. What is this called? domounts.h. I don't know. Where are we? We are in init. Can we find init? Here's M, L, L, M. Maybe this is too much. This is too giant of a commit. I think this is like a release, maybe a release merge or something. Okay, but we can at least look at the let's unblame. Do they call removing blame normal view? Okay. Okay, so let's see, what is this mount doing? This mount do mounts. It creates dev, which I guess is the device. Config if config block dev ram is here. Then we're gonna load some stuff. Let's see. RD load disk. Is this read? Init RD load. Okay. I don't know. So what if we look at the do mounts? Callback for finding a partition using its UUID. Okay, we have a block device. Dev to bdev. I don't know what bdev is. So we check some metadata and compare it to some other stuff. Match dev. So it returns an int. It turns one of the device matches. Okay. Looks up the dev t of a partition by its UUID. Match dev by label. Okay. This is more the sort of thing I was expecting to see in do mounts. Mount NFS root. Okay. So it's going to declare some stuff. NFS root data. Where's root dev? Oh, this is just an argument being passed in, right? Or not? All right. This is an interesting comment. Okay, so we've got dev NFS represents the root NFS, and dev.disk/disk name represents the device number of disk, and then we get partitions. Okay, this is familiar from how Linux works. It's interesting, or to see like where it takes place in the code. Okay, cool. Mount block root. Let's see. We've got a page. We've got to alloc a page. We get. Let's see. We get fs names by calling page address on page. And we do whatever scan printf is doing. This looks like an error message, unknown block. Major root dev, minor root dev. Let's see where the major and minor macros are defined. Are they defined in this file? No. Okay. Cool. All right. So this is pretty interesting. IPC. So there's an IPC syscall, syscontrol. There's an MQ, a message, message util, namespace. I'm not sure what a sem or shum is. Then we have syscalls. Okay. So we're in IPC syscontrol. Do invec minimax, min-max orphans. I don't know. There's a control table that's got a bunch of. So we've got, let's see what we've got. We've got a proc handler. And what are the, is this pointing to functions? Where did the proc handler go? Okay, so let's just grab one of these and see if we can find it in this file. No. Let's see if we can find it in the code base. Can we find maybe a subset of it? Apparently GitHub won't search files that are bigger than like somewhere around 380 megabytes. So a large enough file will just not show up on GitHub search. Okay, what about, okay, so I'm not sure exactly what a proc handler is, but I suspect it's pointing to something like a function. So do we have proc IPC anywhere? Okay, yeah, so here we have proc IPC do int vec min max orphans. And that is a function. So I believe that this table is essentially kind of doing a sort of dispatch where you give it a message that has some sort of name, a proc name, and there's some data, and essentially it chooses a handler. It's like kind of like a routing table. It's got max lengths, modes. I'm not sure what the mode is, but I'm sure they have meanings that are defined somewhere. And then extra, I guess this is kind of like metadata. All right, cool. Okay, so what is this? This is MQ. This is the POSIX message queues file system for Linux. All right. So what's a POSIX message queue? The usefulness of POSIX message queues. Yeah, I know what Linux is and I know what IPC is. Okay. Let's see. Linux provides a platform that supports several IPC mechanisms such as pipes, FIFO, message queues, shared memory, semaphore, and socket programming. Okay. Let's see. Both the named pipe and unnamed FIFO pipes are half duplex and have zero buffering capacity. If a developer needs to store message-based information and later wants to retrieve it, then we have to use message queues. Okay, so it's a queue that you can do IPC with, I guess. You can store messages in it as a sort of buffer. Is what I'm taking away from that blog post. Okay, we've got some inode info, a bunch of structs. Message insert. So where's the actual queue, I guess? While something, the RB entry, is RB entry, if likely, what is likely? Leave priority equals blah, blah, blah. Go to insert message. Go to, huh. That's kind of funny that they use go-tos. Is that necessary to use go-tos? How it might be necessary. Like the world I live in of writing application level services, we don't use go-to. But maybe if you're hacking on the kernel, then you do have to use go-to. Go-to insert message. Let's see what this says. The existing implementation of the POSIX message queue send and receive function is well abysmal. So this was written, like 12 years ago, 11 years ago. So this is hopefully, I hope it's no longer abysmal. So we're going to increase the queue limit. My customer needs help with that too, blah, blah, blah. So who wrote this? Okay. But does this tell you where the go-tos come from? Okay, well, this seems to add all of the go-tos, but I'm not sure if this message is going to tell me. It's going to tell me why they're using go-to. Okay. I don't know. Maybe somebody has commented on this. When it exits from multiple locations. Centralized exiting of functions. Albeit deprecated by some people, the equivalent of the goto statement is used frequently by compilers in form of the unconditional jump instruction. The goto statement comes in handy when a function exits from multiple locations and some common work is done, such as cleanup. In some common work, such as cleanup, has to be done. There is no cleanup needed, and just return directly. So this is kind of like this, I guess, is kind of like what deferred in Java does, or what is it called in Golang? I think maybe it's called just defer. I suspect that they're basically using this, using it in that way. It goes to some finalizer. So okay, go to out free buffer. Okay. Choose label names which say that the goto does and why the goto exits. An example of a good name would be out free buffer. If the goto frees buffer. Okay. Avoid using GW basic names like air1 and air2, as you would have to remember them if you ever add or remove exit paths, and they make correctness difficult to verify anyway. The rationale is unconditional statements are easier to understand and follow. Nesting is reduced. Errors by not updating individual exit points when making modifications are prevented. It saves the compiler work to optimize redundant code away. I'm not sure that those are, from a safety perspective, I'm not positive those are, that completely makes the case for the havoc that can be caused by goto. But I'm also not sure that there's ever really been a goto based Linux kernel bug. So maybe I'm just going to assume in general that they know what they're doing. All right. So that's message queue. All right, here's message.c. I assume this is the thing that goes in the message queue. And so I'm going to not dwell on that. Namespace. This is like an IPC namespace. I don't know if this is the same as the like C groups namespace. I'm guessing it's not. All right, free IPCs. Free, all IPCs of one type. The namespace to remove IPCs from. The table of IPCs to free. Okay, so these are IPC namespaces, and they, I'm going to assume that they do exactly what you would expect them to do. They provide some sort of kind of like mailbox handles so you can send messages to a particular namespace, and others will ignore it. All right, what is this? SEM. I'm just curious what SEM is. SMP threaded, sys controls added. Okay. Namespace support. OpenVZ Swaft. All right. This file implements System V semaphores. User space visible behavior. FIFO ordering for a semaphore. Oh wait, what is this? Oh, this is semaphores. Okay. Cool. One semaphore structure for each semaphore in the system. It's got a semval, a sempid pending alter, pending single SOP operations that alter the semaphore, pending single SOP operations that do not alter the semaphore. Okay. Consolidate. Candidate for sem o time. Huh. Okay. One queue for each sleeping process in the system. So we get a sem structure for every semaphore. We get a sem array for each set of semaphores. That can't possibly be true. Are they mutually disjoint sets? It can be one data. Right. So there can be one data structure for each set of semaphores, because you can create arbitrary sets of semaphores. So maybe a set of semaphore has to be constrained in some ways. So like a set of semaphores that all belong to one process, or that all go together in some sense. But I'm not sure what that means. One queue for each sleeping process in the system. So when the process goes to sleep, I guess. So does sleeping necessarily mean waiting on a semaphore? I'm not sure. So each task has its okay. Sem queue. So what is on the sem queue? A list head, a task struct. This process. Okay, so task struct is the sleeper. So the queue holds, I guess, essentially a pointer to the sleeping process. Undo structure, sembuff, array of pending operations, and the operation that is blocked. Okay. So that kind of makes sense. Each task has a list of undo requests. They are executed automatically when the process exits. All right, cool. Locking. Global semlock for read-write. Global or semaphore semlock for read-write. What is special? Memory ordering. Memory ordering is enforced by using spin lock and spin unlock. Okay, so this is kind of like guidance for, or at least an explanation of maybe the semantics of locking. Okay, cool. I'm not going to dig into semaphores because I don't think that's. I think to understand something like semaphores, you want to read a design document, the semaphore document. I don't think it's. I don't think you want to try to read through the code and try to figure out exactly what it's doing. I am curious what SHM is, though. We got namespaces support. This is kind of like a history of the file. It says better IPC lock. Better IPC lock handling. Okay. We have a Schmid kernel. So we're still on IPC, right? Yeah. Okay, so this is something IPC related. Maybe the right thing to do is just to look it up on the internet. Shared memory virtual file system, maybe? Okay. All right, I'll read this. I'll also read this later. Okay. So this seems to be related to shared memory. Oh, yeah, okay. I remember shimget and shimat. Two variations called shim and tempfs. They both share core functionality and mainly differ in what they're used for. Shim is used by the kernel for creating file backings for anonymous pages and for backing regions created by shimget. Cool. All right, syscalls. All right, so ksys IPC. So we've got a big switch statement, each ending with its return, and what are we switching on? We've got semop, which I assume is a semaphore operation of some sort, semtime, dop, semget, SEM control, message send, message receive. Okay. Syscall defines 6 is going to be is a macro that really just calls this return statement. It defines a function with a single return statement. I'm not sure why you need a macro, but I guess it makes the code a lot more readable and uniform. Okay. Cool. So let's just see if we can find the Linux kernel documentation. Okay. At a high level, system calls are services offered by the kernel to user applications. They resemble library APIs in that they are described as functions with a call name, parameters, and return value. Yeah? Okay. Yeah, I don't think I've ever used a syscall, but my understanding is that it's just a way of calling into the kernel. Okay, here's C groups. Okay, what is this? This is Linux/kernel BPF. I think is something that's relatively new. Debug, DMA. You know what? Let's send kernel to its own browser window and come back to it. I kind of want to process some of this other stuff. So what's in lib? In lib we have more crypto, dim fonts. I'll look at fonts. Live patch, LZ4, which I assume is the compression algorithm, MPI, RAID 6, Reed Solomon, which must be the encoding, bucket locks, B trees, B search. What is bug? I'm just going to look quickly at this stuff. There's simply just too much here for to go through in any depth. Oh, hey. My bit rate is lagging super hard. How do I fix that? So I've reduced the bit rate a bunch. Thanks for telling me. I can see, I'm not sure what happens if I change the bit rate live. It could cause everything to crash. So maybe I won't do that, but I appreciate you pointing that out, and next time I'll experiment with some more bitrate settings. Is it unwatchably lagging? All right. So I'll keep an eye on the chat better. Okay. Okay, so what do we got here? String. Yeah, I'll look at string. Wait a minute. Okay. So I actually have a feeling, with respect to the bitrate, I have a feeling that what's going on is OBS is not using my my GPU to encode, and so I think that even though I have a pretty beefy CPU, it's not it's taxing the CPU to encode at my monitor rate. I think I can try decreasing the video bitrate. Let's try that. So, am I still connected? Hopefully I'm still connected. We'll see how that goes. And I believe that I added a delay. That I think should help the bitrate, but we'll see. I probably have to improve. I probably have to improve the networking situation to this machine, which I just haven't done yet. All right, so let's hope that that slightly fixes things. Okay. All right, random. We've got radix tree. Okay, so let's just look at a couple of these. Fonts. So 6 by 11, 6 by 10, 8 by 8. So are these just font sizes? Font data. These are just like large tables. Okay. Huh. Okay. So I assume that all of the fonts are kind of like this. I'm not sure really what's going on there. But at some point, maybe I can learn about what's going on with fonts. Okay, where are we? We're in math. Cordic, GCD, I assume is the greatest common denominator. Yeah, okay. Prime numbers. Huh. Does it need this for crypto? So Broadcom Corporation contributed Cordic. Cordic calculates the I over Q coordinate for a given angle. Theta is the angle in degrees for which I over Q coordinate is calculated. In coord is the function output parameter holding the I over Q coordinate. Okay. Sounds good. This implements the binary GCD algorithm. Okay. This is least common multiple and prime numbers. So we're, let's see, let's grab one of these functions and see if we can find out, where in the kernel is expand to next prime called? I'm going to guess that it's called in crypto. Oh my. Come on, GitHub. I guess I could just grab the code, but I don't feel like cloning this source tree. Let's see if I can find anything else. How about dump primes? How about is prime number? All right, no code matches. Okay, well then, I give up. All right, bucket locks. So we're going to allocate an array of spin locks to be accessed by a hash. Okay. Allocate an array of spin locks to be accessed by a hash. So what does that mean? Like a hash? Oh, yeah. So the spin locks will be stored in the hash table. Okay, so two arguments indicate a number of elements to allocate in the array. Max size gives the maximum number of elements to allocate. CPU mult gives the number of locks per CPU to allocate. Okay. So one thing that's also weird is that OBS has this Twitch integration, and I get these chat window docs, but they disappear. Like the chat disappears if I take focus away from OBS, which doesn't seem like that's what you want. Let me see if I can. Oh, okay, if I dock it inside of OBS, then I guess it stays there. Okay, so hopefully I won't miss chat messages as much anymore. All right, so hash table of spin locks, I guess. Cool. All right, B tree. This is, I assume, just a B tree implementation. Relatively simple B plus tree implementation is written as a learning exercise to understand. Okay, it's written as a learning exercise. So why is it in the kernel? Hopefully it's more than a learning exercise by now. B plus trees can be used similar to Linux radix trees. But are they used? I'm not sure. Okay. So originally from some guy from Red Hat, Peter Zylstra. All right, B search. Is this searching for? Oh, this is binary search. Okay. Cool. What is bug? Emit bug traps. Nothing happens without this. Generic support for bug. Implement bug and optionally bug on warn. Or is this just like debug symbols? All right. Implement bug to generate faulting and to generate a faulting instruction. So this is like injecting. This is maybe like error injection. So we're going to inject bugs into the kernel. Maybe. Module bug finalize. Report bug. In the illegal instruction trap handler, typically verify that the fault was in kernel module and call report bug. Report bug will return whether it was a false alarm, a warning, or an actual bug. Let's take a look at report bug. Okay, so it's going to take a bug address and point PT regs, or pointer to regs, I guess. Bug entry. If is valid bug address, return bug trap done. Find bug. It'd be nice to have a function. It would be nice to have a function find bug that finds your bugs for you. So we've got a bug entry, and we're going to look in a bug table for the bug address. Okay, so it must be keeping a table of bugs somewhere. I'm not sure what that's up to. String, is this just a Linux specific implementation for strings? This file should only be used for library routines that may have alternate implementations on specific architectures. Okay, so this is this seems to be a string implementation that's designed to work around differences in architectures. All right, here we have a radix tree that was not written as a learning exercise. There's a variable height radix tree. So an insert operation not only has to build the branch to its corresponding item, it also has to build the branch to existing items if the size has to be increased by radix tree extend. Okay. Cool. Net. This looks like it's going to be a beast to go through. So maybe I'll give net its own. I'll do that at another time. Security, app armor. Okay, app armor is built into the kernel, which I guess I didn't realize, but makes sense. SE Linux. I'm not so clear on the difference between SE Linux and app armor. I don't think I'm going to dig too much into these either, but I am curious about them. So this may be something else I come back to. Keys, landlock. What is landlock? Smack. I feel like I have to look at smack. And then security.c. What is security.c? Let's see. It's got some lockdown stuff. Boot time, LSM, user chooser. I don't know what LSM is. Linux kernel LSM. Linux, it's okay, it's Linux security module. Okay. Yeah, I'll read that later. So in here we got app armor, load pin, SE Linux, Mac. We can read SMAC is the simplified mandatory access control kernel. Okay. Just curious, how big is the AppArmor documentation is pretty small. All right. So I'm not sure what landlock is. Was that in the list of security modules? If I just search landlock here. Nope. Oh, there we go. It just took a minute. Landlock LSM. So it creates a scoped access control that is sandboxing. To harden a whole system, this feature should be available to any process, including unprivileged ones. Okay, so it's some sort of sandboxing. So this is SMAC. I guess I don't need to look at SMAC. Sound, I'm going to have to come back for sound. Tools, I'm not sure what's going on in tools, but I want to get to the other directory. User. There's not a lot going on in user. That's a little bit surprising. Is this just like user contributed files? Headers, check. Okay. I don't know. So vert. We have KVM and lib. So how much stuff is in KVM? I guess not a lot. Is there more to KVM? No, come on. Nothing found in the code. All right, GitHub. Okay. Coalesced MMIO, binary stats, async PF. Yeah, there's barely anything here. So I'm wondering if maybe maybe there's more source somewhere else. I don't know. I guess that's another question for another time. I do want to look at this Linux/Linux directory. I think I gave it its own. Oh no, /kernel is the thing I gave its own browser window to. So let's look at what's in /kernel, and then I think we'll break it off. All right, we've got DMA, events, futexes. I forget what gcov is. IRQ, locking, power, print case, sketch, time, trace. So I'm just going to click on some of this audit stuff. Context tracking, crash core, crash dump. Yeah, let's look at crash dump. Groups, hung task, IRQ work, kcov, k headers, panic. Let's look at the panic implementation. Reboot, signal, stack trace, sys, and user, I guess. And then that should give us pretty broad coverage. So in DMA, let me remind myself what DMA is. That direct memory access, I think. Memory mapping. Okay, so I think this is direct memory access. So what is a pool? I guess this is a pool of memory. Atomic pool expand. Memory in the atomic DMA pools must be unencrypted. The pools do not shrink, so no re-encryption occurs in DM directory. Okay. So contiguous memory allocated for DMA mapping framework. The continuous memory allocator makes it possible to allocate big contiguous chunks of memory after the system has booted. Why is it needed? Various devices on embedded systems have no scatter-getter, and or I/O map support, and require contiguous blocks of memory to operate. They include devices such as cameras, hardware video, coders, etc. Okay. Such devices often require big memory buffers. A full HD frame is, for instance, more than 2 megapixels large. That is more than 6 megabytes of memory. Okay. So this allocates contiguous memory in the DMA system. All right, events. Maybe core? Let's look at core. All right, remote function, task function call a function on the CPU, perf context unlock. So call a function on the CPU on which a task runs. Task function calls the function func when the task is currently running. This might be on the current CPU, which just calls the function directly. This will retry due to any failures, blah, blah, blah. Okay, so what am I looking at again? Core, events. Okay, so this is on task CTX scheduling. You can disable the scheduler hooks. Event function call. Event function local. Update perf CPU limits. So I'm just curious what constitutes an event versus something else? Like, is there how do they decide what's an event? Perf clock. Is there like a list of all events, state-based timekeeping? I don't know. Okay, so these are all seem like valid events: calling a function, C group, switching, changing perf stuff, updating various things. Okay. I'm not going to look too much more at that. Okay, so futex is, what is a futex? They're like, I forget what the few is. Is it some sort of mutual exclusion? Let's look up futex. Fast user space mutex is a kernel system call that programmers can use to implement basic locking. Okay, so this is something that user space can call to get access to a lock. So does that mean that there's a futex state has a list head list and an RT mutex base pi mutex. Okay. So we've got hash bucket shared by all futex keys that hash to the same location. Okay, so we've got the hash bucket thing, hash bucket of locks. A hashed futex queue entry, one per waiting task. So this is the waiting thing that we looked at before, but in the land of futexes or futices. I'm not sure. Another futex queue. So what is the underlying implementation? Is it the spin, right? Is that the underlying thing? Double lock. So we've got it spin locks, spin lock nested. What else do we got? No SEMs. But we also, I think we had mutexes. So RT mutex. I'm not sure what RT mutex is, but is it here? Locking. Here's mutex. Okay, here's RT mutex. Oh, is it real-time mutex? A simple blocking mutual exclusion member. Exclusion locks with PI support. What is PI? What does the RT stand for? It's a sleeping log type. Is it real? I don't know. I don't know what RT mutex is, and I don't think it's going to tell me. But we do get an RB tree. All right, cool. We get clang.c. So what is gcov? Profiling infrastructure declaration. Okay. So GCC internal definitions. Yeah, so gcov is profiling info, I believe. The gcov structures can change, as for example in GCC4, blah, 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 blah. All right, IRQ is, I guess, interrupt request. Does that sound right? Spurious, proc, PM, MSI, migration, matrix. What is matrix? It's an IRQ matrix. Is that just a matrix bit, alloc start, alloc size? What makes this a matrix? IRQ matrix. I don't know. Are you sure this is a matrix and not just a struct? We've got a bunch of unsigned ints. We've got a struct CPU map and some longs. Scratch map. Maybe the map is the underlying matrix. But that's fine. So hibernate, main power. These are the things that I guess I would need to know if I wanted to understand why my sleeping on Linux laptops is sometimes buggy. Okay, we've got hibernation modes, hibernation set ops, system entering hibernation, return entering platform hibernation, platform begin, call platform to start. What is platform? To start hibernation, platform, hibernation platform. Is this like an enum? I don't know. All right. Print elapsed time between two events during hibernation. Arch, resume, no smut. Platform finish. Are these more go-tos? I think these are go-tos. Yeah. Okay. Bug on. Huh. Oh, is bug for the above should either succeed and jump to the new kernel or return with an error. Otherwise, things are just undefined. So let's be paranoid. So I guess kind of the point of bug is to it's like a way of failing that records buggy behavior. Okay. So this hibernate stuff actually looks pretty complicated. There's a lot of if statements, a lot of go-tos. Check if the device is there. Like I think a lot of edge cases. Hibernation can be handled in several ways. There are a few different ways to put the system into the sleep state using the platform driver. Okay. ACPI or other hibernation ops, powering it off or rebooting it. The sysfs file, syspowerdisk, provides an interface for selecting the hibernation mode to use. Okay. Cool. Image size restore. We're just going to scan a buffer. Okay. Image size show. Resume setup. If no resume, return one. Yeah, I don't know. This is This looks kind of a little bit on the complicated side. And like there's a lot of different options that you could branch from one place to another. Just curious how old the code is. 4 years ago, 18 years ago. Okay. All right, power main. Unlock system sleep, lock system sleep. Unregister PM notifier. PM async store. Decode suspend state. Mem sleep store. Okay, kind of the same thing. There's a lot. Case freeze, prepare, suspend. Suspend no IRQ, resume no IRQ. Suspend stats show. PM print times. Decode state. The wake up count attribute, along with the functions defined in driver/base/power/wakeup.c, provides a means by which wake up events can be handled in a non-racy way. You don't want racy. You don't want to have your wake up events be too racy, at least not on your computer. If a wake up event occurs when the system is in a sleep state, it is simply woken up. In turn, if an event that would wake the system up from a sleep state occurs when it is undergoing a transition to that sleep state, the transition should be aborted. Okay. All right. So this, again, this looks, I don't know what the word is. None of this looks wrong or bad or anything. It's just with all of the conditionals and kind of like if string has prefix, like what is length equals 4 and string has prefix, that it's just a little bit hard, certainly as an outsider to look at and read. But my guess would be that even if I knew, even if I were a kernel hacker, I would have to, that this code would be like maybe a little bit on the harder to read side. And that might be intrinsic to the problem space. There are just some problem areas where code is just going to be more complicated in various ways. And this, power management is quite possibly one of them. I don't know enough about it to say for sure. Okay, what is this? This is power.h. I suspend. I am assuming it looks pretty similar to hibernate. This actually looks a little bit cleaner. This looks like this starting to look like Golang code. If error do this, if error do this, if error do this. Okay. Yeah, this file for whatever reason looks a bit cleaner to me. Okay, wake lock. User space wake up sources support. User space wake up sources support. Okay, PM show wake locks. And so is a wake lock something that wakes you up when you have the lock, when it's your time? Oh, it locks sleep. Is there a Wikipedia page? Wake lock redirects to Android. So that seems like it's going to be hard to search for. So I'm giving up. All right, user.c. This file provides the user space interface to software suspend resume. Okay. That's fine. I'm done with power for now. Okay, so here's time. We have namespace, NTP, POSIX stubs, tick legacy, time.c, and timer.c. Do we have a non-legacy tick? Tick common? Maybe tick schedule? All right, this is time.c, contains the interface function with various time-related system calls. like get time of day. Okay, so we're defining a bunch of syscalls, and let's say kernel old time. Let's choose something small. So we're going to declare an I, and we're going to call get real time seconds and cast it. And if tlock, I guess, is some sort of timer lock. And then we're going to try to put the user, I guess, on the lock for successful syscall return. Okay, so that's actually a pretty straightforward function. Timer, we've got some trace points. This is a monster comment. Look at that. The timer wheel has LVL depth array levels. Each level provides an array of LVL size buckets. Each level is driven by its own clock, and therefore each level has a different granularity. The level granularity is level clock div, I guess, XORed with level. The level clock frequency is this thing. The array level of a newly armed timer depends on the relative expiry time. The farther the expiry time is away, the higher the array level, and therefore the granularity becomes. So the farther it is away, the higher the array level and the granularity. So is this saying that, like, as the timer approaches being done, we're going to, I guess, promote it up a level? So if a timer is like a few milliseconds away from going off, then the maybe nanosecond granularity matters. But if a timer is like a month away from going off, then you don't need to keep track of nanoseconds. Is that the sort of thing? Okay, here's a table. So at level 0, the granularity is 1 millisecond. At level 8, granularity is about 4 hours. Okay, so that does seem kind of like what they're up to. All right, that's kind of a cool idea. I wonder how common that is. All right, tick common, tick devices. Tick next event keeps track of the tick time. It's updated by the CPU, which handles the tick, and protected by Jiffy's lock. There is no requirement. What is Jiffy's lock? To hold the Jiffy's sequence for it. Okay, cool. So this is the tick is basically handled by the CPU, which is kind of expected. Tick scudge. I don't know what a Jiffy's lock is. So I'm looking at jiffys.h. The following establish the engineering parameters of the PLL model. The HC variable establishes the timer interrupt frequency. Okay, so whatever Jiffy's is it seems to be locked. It seems to be timer and time specific. Kernel trace, backtrace, BPF trace. There's a bunch of stuff here. I guess I'm going to go through that later when I go through another pass that looks at things like BPF maybe. Audit tree. I would look more into this, I guess, when I'm looking at the security stuff. One struct chunk is attached to each node of interest through audit tree mark. So we've got some tree. Cyclic lists galore. Okay. I'm going to mostly ignore this for now and come back to it later. Context tracking. Probe on high-level context boundaries such as kernel, user space, guest, or idle. This is used by RCU to remove its dependency on the timer on the timer tick while a CPU runs in idle, user space, or guest mode. Okay, so I guess this is tracking some tick-related stuff and is tracking something about the boundaries between like user space and kernel space. Okay, so stores the physical address of the elf header in the crash image. So this is crash stuff. And It seems to be ELF specific. So we have, what is groups? So we're in groups.c. Is groups like Linux groups, like related to users? Set current groups, change current group subscription. Okay, yeah, this kind of seems like Linux groups. Set groups. Okay, it's nice to know where this is, but I'm kind of just sprinting to the end here, I think. Okay, kcov. Kcov descriptor 1 per debugs file. Share transitions in the descriptor. I don't know what kcov is. Is this more performance stuff? Stop this. Coverage for fuzzing. Kernel code coverage information in a form suitable for coverage guided fuzzing. Randomized testing. Okay. So this is like test coverage. I am curious to see how that looks, but how that works. But not right now. Okay, so panic. So we've got some ways to configure panic, and oops, all CPU backtrace, warn count show, no blink. Stop ourselves in NMI context if another CPU is already panicked. Arch code may override this to prepare for crash dumping, e.g. to save register info. Stop other CPUs in panic. Architecture dependent code may override this. Okay. So, panic. Halt the system. The text string to print. Display message. Okay, so panic is going to allocate this buffer, give some variables if panic on warn. The thread may hit another warn in the panic path. Resetting this prevents additional warn from panicking the system on this thread. Okay, so we're setting panic warn to 0. Going to disable IRQ locally. Preempt disable no trace. Okay. Only one CPU is allowed to execute the panic code from here, so we're going to get a processor and execute some panic code. And this KGBD panic, if crashed kexec, atomic notifier call chain, run any panic handlers. So there are, I guess, a chain of handlers that you can call when you're panicking. Panic print sysinfo false, and then we're going to, I guess, dump the panic message. If you doubt, kdump always works fine in any situation. Crash kexec post notifiers offers you the chance to run panic notifiers and dump kmessage before kdump. All right. And then some more stuff. Okay. That's actually pretty interesting. All right. Reboot.c. This indicates whether you can reboot with Control-Alt-Delete. The default is yes. All right. Static int CAD is equal to 1. Export simple CAD PAD. Okay. So we've got prevents linkage failure while we're in process of removing all uses of legacy PM. This is just, I guess, code cleanup. We have emergency restart. We're going to dump the kmessage dump the identifier for emergency restart. Then we're going to call machine emergency restart. Kernel restart prepare. So if it's not an emergency, I guess we're going to do blocking notifier call chain and I guess notify everyone that's subscribed to the reboot notifier list. And then set the system state to shutdown, user mode helper disable, and device shutdown, and call the device shutdown function. It doesn't seem to grab a lock, so I'm not sure if if the system state variable is readable to other people. Okay. Signal.c. Oh, this is like kernel signals, right? Okay, this is actually interesting, but again, I'm just trying to get allocate a new signal queue record. This may be called without locks if and only if t is equal to current. So we've got a signal queue. We can flush the signal queue, flush signals. Okay, task participate group stop. Task clear job control pending. Why is bug on called? Bug on mask. Job control pending mask. And there's this ptracer stuff. Okay. Stack trace I'm going to ignore. I'm just curious what's in sys.c. We've got get endian. Is this like customizations for specific systems and architectures? This is where the system-wide overflow UID and GID are defined for architectures that now have 32-bit UID, GID, but didn't in the past. Set the priority of a task. The caller must hold the RCU read lock. We're going to define some syscalls like set priority, get priority, okay. Unprivileged users may change the real GID to the effective GID or vice versa. Okay, so this is like UIDs, GIDs, that sort of stuff is defined in here. Cool. And what is user.c? The user cache. We have a per user structure to keep track of how many processes, files, etc. the user has claimed in order to be able to have per user limits for system resources. So is this like, so we're going to init the user namespace, UID hash find, UID hash remove, user epoll free, IRQs are disabled and UID hash lock is held upon function entry when you call free user. Okay, so this seems to be, like we looked at groups before, this seems to be the implementation of users for the kernel. Okay, so that was a lot to kind of go through all at once, especially not having a lot of, for me, not having a lot of context going in. I'm definitely going to come back and look at more specific areas of the kernel that I think bear understanding, where I think it would be fruitful to have a better understanding of what's going on. Things like C groups. I'm curious to understand more about how audio and video and networking work in the kernel. Those are kind of places where the computer interacts with the outside world in various ways. But you know, I have a better sense of how things are organized, and also what the style of the kernel code is. And I'll leave it there. Thanks.